Grigori Avramidi from Münster.
Okay, thank you. It's very nice to be in Cambridge. Is this working? Okay, all right. So I'll talk about ends of non-positively curved manifolds. This talk is joined with Tam Nguyen Phan. And first, let me start by telling you what kind of manifolds I'm talking about. So I'm always going to look at complete Riemannian manifold of bounded non-positive curvature, the curvature between 0 and -1, and finite volume. So in particular, I will be mostly interested in manifolds that are non-compact, but they have finite volume. So the schematic picture of such a manifold is something like this. It's something that has an inside and an end or a cusp, this region over here. And I won't precisely say what an end is, but it's something like this. And in nice cases, it will look like a closed manifold cross array. It'll be homeomorphic to a closed manifold cross array. And so if your manifold is non-positively curved, when you look at its universal cover, so this is going to be my picture of the universal cover. This is the manifold M. This is M tilde. Let's say I have dimension n. Right? It's going to be homeomorphic or diffeomorphic to a disk. And then you can also look at what lies over this end upstairs. And for now, I'll just draw some awful-looking picture. So this yellow region is just whatever is lying over this end down here. And then the vague question that I want to discuss is, what can we say about the topology of the end? So what can we say about either the topology down here or the thing that's lifted to the universal cover? So let me begin with an example that, well, that we probably all know, and that's of a non-compact hyperbolic surface. So this is example 1, maybe even example 0. Hyperbolic surface. So I'm going to draw a picture of that, and the picture is going to look, well, the picture will be the same, but now it's less of a heuristic picture and more of an actual picture. It's still not quite an actual picture because I can't draw a hyperbolic surface on a plane. Right, but so this is a punctured torus with a complete hyperbolic metric on it. And in this case, it's non-compact, but it's non-compact in a very, very mild way, in the sense that this end literally looks very, very nice. It's just a circle cross array. It's homeomorphic to a circle cross array. And if you look at its universal cover is hyperbolic 2 space, H2. And the things that the things that lie over this end are these disks that touch the boundary in the Poincare model of the hyperbolic 2 space, which are called horoballs, or in this case maybe horodisks. And they're disjoint, and there are infinitely many of them, but I'll only draw this many. And they're all they're all disjoint, and that's somehow that's all there is to say about a hyperbolic surface. Well, that's all that I'm going to say about a hyperbolic surface. Sorry. All right. So the next example is what happens when you take a product of two such surfaces. So product of surfaces. So if I take two such hyperbolic surfaces and take the product, a nice way to draw this is by the following picture. It's to draw it like this. And this picture, one thing it sort of emphasizes is that, well, whereas here there is just one way to go to infinity, essentially just one way to go to infinity, here there's really a whole sector of ways to go to infinity. You can go this way, or somewhere in between. So on a large scale, this looks like a sector, whereas that just looks like a ray. And you can try to understand, so what's such a manifold? Right, so this manifold is a punctured T2 cross punctured T2. And this now has a non-positively curved metric. It has flats because it's a product, but it has a non-positively curved metric. So it's a manifold like this. And the end here also has a nice structure, but now it's covered by pieces. There's one piece that looks like this, and there's another piece that looks like this. And my manifold is still, well, it's the interior of a compact manifold with boundary. The end looks like a closed manifold cross array. But now this closed manifold has extra structure. It really is made up of two pieces. One piece that looks like a surface with a torus with a disk cut out across S1, and the other piece, this piece, which looks like an S1 cross such a torus, and they're glued together along a two torus. Right, so this is that's what that end looks like. So, right, so it's a graph manifold. Anyway, so that's what's going on downstairs. And upstairs, if you look at the universal cover of this, well, so the universal cover of this is H2 cross H2, but I will actually just draw it as a 4-disk. And in this universal cover, I can look at what happens to lift of these kinds of pieces. And there are actually infinitely many of them, but I'll just draw two. So this is one, maybe this is another. They're all mutually disjoint. And then I can also look at what happens to lifts of these kinds of pieces, and there are, again, infinitely many of them. And, well, so the picture looks sort of like this, except to make it slightly less deceptive, let me maybe make this disk look higher dimensional. So this is, again, there are more things like this, but the thing that I want to emphasize is that when you look at what's lying over the end, there is some topology here that comes out of the overlap between these different pieces. Okay, so that's the second example. That's the product of surfaces. Puncture T2 across T2. And the third example is, well, locally symmetric spaces of non-compact type. So these are things, I mean, I'm not going to give a definition, but these are things that are of the form G mod K mod gamma. And the thing that you should think of is something like this. You should think of maybe SL3R mod SO3 mod, well, I want to write SL3Z, except there is a slight issue here because this has torsion, so I'll put a prime here, meaning that I take a finite index torsion-free subgroup. So these are somehow a large class of manifolds that are very well studied, and they're all of this sort. They're complete Riemannian, non-positively curved, and finite volume when this gamma is a lattice. And so such manifolds, so they have a similar structure. I mean, somehow there's a much more complicated picture, but in some sense it's schematic. Well, it's qualitatively quite similar to what happens for a product of surfaces. So I'll draw some picture, which I guess looks like this. So it's a manifold. There's some topology on the inside, and then there's some sort of pieces that the end is made out of. They're finitely many, well, maybe a finitely many types. And when you look at the universal cover of this manifold, then again, so this is my manifold M. This is its universal cover, M tilde. It happens to be, right, it's still a disk. And if you look at what's lying over these pieces, then, well, it again has some overlap, some topology. And what I want to say is that a lot is known about what the topology of the thing that's up here is. In fact, one knows that it's always homotopy equivalent to a wedge to an infinite wedge of spheres of a given dimension. The dimension is called Q minus 1. And so this Q is often called the Q rank, at least in cases when these are sort of rationally defined. And so one thing, I mean, by looking at what are the different types of locally symmetric spaces, one thing that one finds is that this Q, so this Q, will turn out to always be less than or equal to the dimension of the manifold over 2. So this is something that one can notice. And in fact, there are cases where it's actually equal. So this is equal if the manifold is a product of a bunch of punctured surfaces. So this picture, I mean, this is somehow where you have a disjoint union of a bunch of disks. So this is the case when Q is equal to 1. So that's a wedge of 0 spheres. Each 0 sphere is 2 points. So that's a confusing way of saying it's an infinite set. when you have a product of surfaces, this is a wedge of one spheres, so it's homotopy equivalent to a graph, so there are infinitely many loops, etc. And in higher dimensions, it's a wedge of higher dimensional spheres. So that's the structure. And so this structure, I mean, this goes by the name of Borel. Sort of this description, and the thing that's going upstairs is essentially sort of the Borel-Serre compactification of locally symmetric spaces. And it really comes out of the arithmetic of something like this. And then a question arises, to what extent is this really determined by the fact that these manifolds are non-positively curved? And so that's what I want to talk about in the rest of this talk. So let me begin by saying, talking about the thick-thin decomposition for non-positively curved manifolds, right? So this is described in terms of the injectivity radius. So recall the injectivity radius. This is a function which, to a point x, assigns the maximum radius of a ball, of an embedded ball centered at x. So B ball centered at x of radius r, so that this is embedded into the manifold. So I'll draw a picture in a moment, but first let me say, so this is the injectivity radius of function, and it lets you subdivide the manifold into a thick part and a thin part, or maybe so there's the thick part, or epsilon to thick part, and this is the set of all points in M, such that the injectivity radius is at least epsilon. And then there is the thin part, M less than or equal to epsilon. That's the set of points where the injectivity radius is at most epsilon. Right, so this is epsilon thick. This is epsilon thin. Now if you draw a picture, again, I keep drawing the same picture. But if you draw a picture, then at a point over here, so maybe this is my point x, and now I look at the ball of radius epsilon, and here I can embed the ball of radius epsilon. So that means this point is in the thick part, and somewhere over here, if I try to embed a ball of radius epsilon, then I will fail. It will overlap itself. So this is something that's in the thin part. And right, so this subdivides the manifold into a, so maybe this is the thin part, a thick part. This is the thick part, and this is the thin part. And, well, this picture suggests that the thick part is compact, and that's in fact true. So if the volume is finite, then this is compact. And this is just because, well, if it wasn't compact, then it would be an unbounded set, and that means you could pack the manifold with infinitely many disjoint balls of radius epsilon, and then that would give you an infinite amount of volume. All right, so that's something about this. And now the question is, what can one say about the topology of this, of the thin part? And, well, so the first thing that I'll tell you about it is the following theorem, which is a theorem of, well, it's a theorem of Gromov and also Schroeder. It's a generalization of a theorem of Gromov and a specialization of a later theorem of Schroeder, which is why I'm putting both names here. Right, and it's saying that if you have an n manifold and it has bounded non-positive curvature, finite volume, and also this condition, which I'll address later, no arbitrarily small closed geodesic loops. So if you have such a manifold, then that means that there is an epsilon such that this thin part is homeomorphic to a closed manifold, you can call it just boundary, cross array. So what is this saying? Well, it's saying, again, starting with the same picture, what it's saying is that if I picked my epsilon and it was sort of not that small, then maybe this thin part is picking up Well, it's picking up some topology that has to do with the end, but maybe it's also picking up some other stuff. But if I keep lowering, if I keep making this epsilon smaller, eventually the other stuff will go away, and I will be left with something that just picks up the topology of the end. And this theorem is saying that once it's just picking up the topology of the end, then somehow this topology doesn't change anymore. It will just look this. It will just look like some specific thing cross array. Okay, so this is saying in particular that this manifold, it's the interior of a compact manifold with boundary, so it's tame. It doesn't have infinitely many ends or anything like that. And so let me address this comment, this condition of no arbitrarily small geodesic loops. So this is also, so this is something that's actually necessary, and this is sort of also a well-known example of Gromov illustrating that this is necessary. And the example is that without this condition, you can build an infinite type graph manifold that has a bounded non-positive curvature, finite volume, etc. And let me just draw a picture illustrating how you do that. So you build a three-dimensional graph manifold in the following way. So each piece is a surface with two boundary components cross S1. But when you take the surface, then you go really, really far into the cusp so that the loop is really, really small. And so that means that, and then you flip. But when you flip, this looks, again, like a surface with two boundary components. But this other piece looks like an S1 that's really, 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 really narrow. Because it's really narrow, it contributes very little volume, and you can keep doing this. And you keep making it smaller, etc. And you do it in the other direction, too. So you do it the same way in the other direction. And this way, you get an infinite type graph manifold, but it has such symmetric. So you really do need this condition.
And what dimensional is that?
This particular example is three-dimensional. It is. So the point is, this loop is really small. That's what's killing the volume. And then here, it's. I mean, you can make the volume look like a geometric series. I mean, this is an S1 that has radius 1 over 2 to the n.
Well, that's a direct product, isn't it?
Yeah. Oh, yeah. So each piece looks like a surface cross S1, but the S1 is getting smaller and smaller and smaller, and the volume of this is bounded above by anyway. So it's right. So you really do need this condition. And on the other hand, this condition is satisfied for some nice types of manifolds. So it's true for all the locally. So it's true for locally symmetric spaces of non-compact type. So they satisfy this condition. It's also true if your curvature is negative, not necessarily pinched, but just you don't have any actual zero curvature regions, then it's also satisfied. So, I mean, it is something that's frequently true, but not always. Yes?
But has this example an infinitely generated fundamental group, right?
Yes, it does.
Is it possible with finitely generated fundamental group?
I'm not sure. It's possible that there are some
Not in 3.
Oh, no, not in 3. Yeah,
not in 3. No, I mean in any dimension. No, not in 3.
I haven't thought about it, but I can try to think about it in a bit. Okay. But anyway, under these assumptions with this additional condition of no arbitrarily small closed geodesics, you do have a nice end. Namely, the end looks like, so the upshot is that this looks like a boundary cross array. Up to, like, it's homeomorphic to something like that. Okay. And in this case, then we can say something about the topology of this boundary. So let me try to say what the main theorem is. And to state the theorem, I need to so the conditions are exactly the same as in this Gromov-Schroeder theorem. And to start to state the theorem, let me start by drawing that picture and its universal cover. Right. So this is the picture. There's an epsilon and sufficiently small epsilon so that this end looks like closed manifold cross array. And then you have yes.
Behind the fun.
Well, this part is not important. The universal cover will be important. So if you can see this part, then it somehow I can live with that. I don't know if you can, but okay. So then this is the universal cover. M tilde, which is like the n disk. Now you look at what's lying over the thin part. So I'm going to start drawing just some overlapping regions. Sorry, I shouldn't do that. So this is the part that's lying over the thin part. And let me call it m less than or equal to epsilon tilde to indicate that that's the part lying over the thin part. And now I want to say something about the topology. Oh, and again, let me draw it so that it looks higher dimensional. And yeah, OK. So now I want to say something about the topology of this region that's lying over the thin part. So by topology, I mean I'm going to look at a homology cycle, or more generally a map from. So this is going to be a map F from a finite polyhedron. So there's some topology, which maybe I'll draw this way. So in this picture, it's going to look like some sort of surface. Right, so it's a map from a finite polyhedron into this thin part. Let me call it F. Then the theorem is that, so this map F can be homotoped. Inside this cover of the thin part. So inside this yellow region, it can be homotoped inside this yellow region to a map. Let's call it F hat that factors through something low dimensional. So I'll say specifically what I mean. That factors through something. That factors through a complex of. So this is n. Oh, I don't know why I'm using green. Okay. N over 2, the floor of n over 2 minus 1 dimensional complex. So in this picture, what you should think of is that this surface, you're homotoping the surface to something that's possibly lower dimensional. Maybe it's something that actually just looks like a loop. And so let me try to state some corollaries of this to illustrate what this sort of thing means, or what this sort of thing tells you. So
What are the assumptions?
So the assumptions are that you have an n-dimensional manifold. It's complete Riemannian. It has bounded non-positive curvature. It has finite volume, and it has no arbitrarily small closed geodesic loops.
And F?
And F, P is a finite complex, and F is a map from P into the thin part upstairs. So that's the setup. And so the consequences of this are, so the first one is that if you look at the homology of this thin part, let me write it this way. The homology in dimension greater or equal to floor of n over 2 of the thin part upstairs, this m less than or equal to epsilon tilde, this vanishes. And this is just because, right, I mean, so homology is represented by maps from pseudomanifolds, from some cycles. And since this factors through something of dimension n over 2 minus 1, that means in dimensions above the floor of n over 2, it factors through 0. So this statement is, well, it's sort of, it's part of this. I mean, right, this is a wedge of q minus 1 spheres. So this is something that's true for locally symmetric spaces, but this aspect of it is also still true for non-positively curved manifolds. And the second thing is, so if you look at the dimension, let me say, if n is less than or equal to 5, so if you're in a low dimensional case, then this tells you that, right, so this is the interior of a compact manifold with boundary. By the way, I mean, there could be more than one component to the boundary. It's just, I don't want to keep, somehow, I'm really good at drawing a surface with one cusp for some reason. But each boundary, so there's more than one component, but each boundary component is, so boundary is aspherical. And again, I should say each boundary component is aspherical, but I don't want to write that. And this is just because, so if your dimension is less than or equal to 5, well, how do you check whether something is aspherical? You look at maps from a sphere. If n is less than or equal to 5, then this is 5 over, the floor of 5 over 2 is 2 minus 1 is 1. So that means this factors through a graph. And therefore, you can contract any higher spheres. So it ends up being aspherical. And then So this is an aspherical, if n is 5, this was an aspherical 4 manifold. If n is 4, it's an aspherical 3 manifold. Then you can ask sort of, well, how bad of an aspherical manifold can it be? And, well, so we can say the following, which is maybe somewhat interesting. And this is not, it's sort of a corollary of the method, but it's not exactly a corollary of this statement. So we can say that if you look at the thin part up here, again, in dimension n less than or equal to 5, the fundamental group of this is locally free. So pi 1 of, again, I should say each component of this cover of the thin part is locally free. OK, so those are a couple of consequences. And now let me also say, right, this and this look like something that are just about the end of this manifold. But you can translate it to something about, well, that's really about the fundamental group of the actual manifold M in the following way. So first of all, the fundamental group, let me call it, so pi 1 M, let me call it gamma. Right, so it's acting on the universal cover. And this statement, and I don't want to sort of go into detail about why, but it's not so hard that using the fact that using things like left-Schwarz duality, etc., this statement gets translated to the following statement. So it gets translated to the statement that the group cohomology of B gamma with coefficients in Z gamma, this is 0, except this is 0 in low dimensions. So in dimension less than the ceiling of n over 2. Sorry. So the group cohomology in dimension less than the ceiling of n over 2 is 0. And if you think, right, so it only shows up in higher dimensions. And if you think about it, if you think about either this or this, you know that there's always some group cohomology in these situations. I mean, I can tell you why. And so a corollary of this is that B gamma, the dimension of B gamma, is at least the floor of n over 2. So it means that these manifolds, so this is somehow a corollary about the manifold M. It means that you can't, it's not homotopic to something less than half dimensional. OK, so that's a list of consequences. So I want to say a few things about where this comes from. And, well, so the first thing that I'll say, maybe, let me start by telling you something that's somehow a naive way to try to do something that doesn't work, but I want to say it to illustrate something. So you can start, so take a geodesic ray that's in the surface. I guess I do need the bottom of this picture. Take a geodesic ray that goes into the end. So you can find a geodesic ray that diverges. And look at what happens when you lift it up to the universal cover. So one of the lifts will be some sort of geodesic ray upstairs. And a naive thing to do is to, say, well, try to push everything to this point at infinity. So all of this topology, the whole cycle, just try to push everything to this point. And if I draw this picture is going to get even more crowded, so I'm just going to use my finger to illustrate that. You're pushing everything here. Well, so the reason why you might want to do this is the following. As you push to a single point at infinity, the size of this cycle, its diameter, doesn't get any bigger. It either shrinks or stays the same. But as you push further and further this way, you're going further and further into the thin part. So there's sort of more room to contract things. So if you go further into the thin part, then the diameter of the cycle, then you can contract it. So that's the good part. The bad part is, of course, when you're doing this, you're pushing it through here, which corresponds to the thick part. So it doesn't really, so that's why it doesn't work. So instead, what you actually need to do is you need to, in an intelligent way, figure out how to push different parts of the cycle to different points at infinity. And then do this in a compatible, so maybe this part this way, this part this way, this part this way, this part this way, etc. And do it in a compatible way so that you can push points and then you can push edges, etc. So that's somehow what one needs to figure out how to do. And then this needs to happen in such a way that sort of at infinity, the cycle collapses to something that's actually lower dimensional. So next, let me try to tell you how one can try to figure out sort of which points at infinity to push to. So I'm going to draw this picture again, except I'm going to zoom into just a portion of it and try to make it less crowded. So this bottom here, this is part of the boundary at infinity. This is the universal cover. And this yellow region this is the lift of the thin part. So this is m less than or equal to epsilon tilde. And let me say, so the first thing to say is that, right, so there's a different way to describe what the thin part lifts to upstairs. Namely, up here, right, you were in the thin part if a ball of radius epsilon did not embed. When you tried to embed, it overlapped itself. What that means up in the universal cover is that there are a pair of translates of the ball of radius epsilon. So there's like some point y and gamma y, and they overlap. And each one of these has diameter epsilon. So the distance between gamma y and gamma y is less than or equal to 2 epsilon. So this can also be written as the set of all points in the universal cover such that the distance between x and gamma x is less than or equal to 2 epsilon for some non-trivial element in pi 1. Okay, that's another way to describe this cover of the thing that's lying over the thin part. So in particular, if I'm looking at this cycle, and I'll draw just, so this is part of the thing that I'm trying to push to infinity. So this point, there's some element in the fundamental group that moves it. So this is some point x. This is gamma x. There's some element in the fundamental group that moves it by less than 2 epsilon. OK. And so now I need to say or remind you of a couple of things about isometries of non-positively curved spaces, or tell you a couple of things about isometries of non-positively curved spaces. Right, so if you're looking at elements of the fundamental group, so there are two types. There are infinite order elements. They're hyperbolic and parabolic. And the hyperbolic elements are the ones for which the infimum of the displacement function. So if I look at elements in the universal cover, the infimum of how much the isometry moves the point, this is attained. That's what it means to be hyperbolic. And in this case, so this displacement is some number L. In this case, if you're looking in the universal cover, there is some geodesic along which you're translating by L. So that's what this isometry is doing. And if you're looking downstairs, it gives you a closed geodesic of length at most L down in the manifold. So if you're parabolic means that this infimum is not attained. And in this case, well, so one can say the following. So one looks at the fixed set on the boundary at infinity. So the set of points on the boundary at infinity that are fixed by this element. And it turns out in this fixed set, you can find a point. So that if you look at the geodesic ray going to that point, maybe I should draw it in yellow. If you look at the geodesic ray going to that point, then downstairs that ray diverges. So this projects to something that actually diverges. And one could actually say something, let's see how much, yeah, okay. One can say something even stronger, namely that, well, so this boundary at infinity, so this is the boundary at infinity of the non-positively curved manifold. So there's this nice metric called the Tits distance, right? And it's defined in the following way, right? So for 2 points in the boundary at infinity, you can first look from some point. You look at these points and look at how far they're apart. So that's this angle at x, and then you can take the supremum over all x, and that doesn't depend on the base point anymore. So this is in some sense better because it's invariant under isometries, for instance. And finally, you can take the path metric. So this thing called the Tits distance is the path metric associated to this. So it turns out that this fixed set, there is a construction, sort of a two-step construction that goes back to, well, Ballman, Gromov, Schroeder, or possibly Eberlein, for this fixed set of a parabolic element for finding a specific point, x gamma, so that the point is described just in terms of this Tits metric, and the fixed set itself is star-shaped with respect to this point, and everything is within pi over 2. So this distance. So this distance is at most pi over 2. This distance is at most pi over 2. So this is somehow a very nice way to pick out a point in the fixed set, and then one can show that for this point, various nice things are true. One of them is that if you take the geodesic, it diverges downstairs. So let me now go back to this picture. So what was the point of that discussion? The first point is that this condition, that there are no arbitrarily small closed geodesic loops, means that when epsilon is sufficiently small, so when epsilon is a lot smaller than the length of the smallest closed geodesic loop, this isometry, it can't be hyperbolic, because if it was, there would be a loop downstairs. So it's really, first of all, it's parabolic. So you can find a point at infinity that is fixed by it. So this is the point x gamma. So this point is fixed by the isometry. And that means that as you push towards this point, well, so it means that if you take the geodesic ray to this point, and you also look at the translate of this geodesic ray, they both go to the same point at infinity. So this distance, it started out being 2 epsilon. It doesn't get any bigger. It always stays at most 2 epsilon. So that's why if you push to this point, you're going to be staying inside the thin part. And also, because that geodesic ray diverges, you're staying inside the thin part, but you're actually going further in. So this is somehow progress. And then this is at one point. You have to do this at more points. So if there's some other, so this was point x, some other point y, then you can play the same game. So this is rho y, some element that moves it by at most 2 epsilon. And it's also a parabolic element. So again, you find a point at infinity of this sort. Now, when these points are close together, then over here, the element gamma is small. Over here, the element rho is small. And in between, both of them are kind of small. Maybe they're not this small, but they're still smaller than 2 epsilon plus some delta if they were close enough. So that means this group generated by gamma, the group generated by gamma and rho, this group is generated by small elements. And then this is somehow why it's crucial to have that the curvature is bounded below. So it's really bounded non-positive curvature. One sort of has a lot of control about what these groups generated by small elements can look like. And it turns out this is called the Margulis lemma. This group is virtually nilpotent. Sorry. So this group is virtually nilpotent. And in fact, well, one knows somehow how virtually. I mean, the index is uniformly bounded in terms of the dimension, etc. So this group is virtually nilpotent. There are some tricks you can do to get from a virtually nilpotent to actually an abelian group. And I don't want to tell you what they are. But so let's say for the moment, I'm going to use your notation and put the word abelian in quotation marks. So let's say this group was abelian. So that means that gamma and rho actually commute. Well, if gamma and rho commute, then what does that mean? Well, that means, for instance, in this picture, this element rho, the fact that rho commutes with gamma means it preserves this fixed set. And that means that it actually fixes this unique special point that serves as the center of the fixed set. So in other words, that means that this element rho would fix both of these points. And that means that this distance is at most pi over 2. And when you have something that's at most pi over 2, this is good. It means somehow at infinity, there is a way to connect them by a geodesic in this Tits distance. So that means that you know how to fill this in and push to infinity. That's what that means. And so doing something like this, you end up getting, so this was my original map F. You end up getting a new map F, let's call it F infinity, that tells you how to push this finite piece of topology, this finite polyhedron, all the way off to infinity. And And it's doing it in sort of a somewhat nice way, because it's staying in the thin part and it's going further and further into the thin part. So as you go further and further into the thin part, there's sort of more space, and there's more space to collapse things down. And so the key thing then turns out to be, the key thing for proving this theorem turns out to be showing that there is a way to do, again, something like this, so that the dimension of the image of f infinity is less than n over 2. Where this dimension is, I mean, again, this boundary at infinity has a Tits distance. It's a dimension it's a Hausdorff dimension in that Tits distance. Okay, and so the last thing that I want to tell you in the last 10 minutes is that, so somehow, the thing that you would think of when you have 2 points that are pi over 2 apart, you would try to connect them by a geodesic. So it's by a geodesic. So this distance is cat1, so there's a unique geodesic connecting them. And that's the thing that you would somehow, as a non-positively curved geometer, that's the first thing to think of. And then if you try to build higher dimensional simplices, you connect by geodesics and then connect those by geodesics, etc. But it turns out that there's actually something else that is better suited for at least this problem. And that is, instead of building simplices using geodesics, so one built what are called Busemann simplices. So I want to give an idea of what that is, and hopefully why one would want to do that. Okay, so the first, if I have a point in the boundary at infinity, and this is a geodesic ray going towards that point, then there's one way, there's something like a distance function to this point at infinity. What do I mean by that? Well, you can look at the following function. H of x is equal to the limit as t goes to infinity of the distance from, let's call this initial point x naught, from x to r of t minus the distance from x naught to r of t. Right, so if I just took this, the distance from x to r of t, and took the limit as t tends to infinity, this, I mean, it looks like the distance to this point at infinity, except of course it's infinite. But if you normalize it in this way, by subtracting this, which is just t, then you get this function, and this is called the Busemann function, centered at this point. And this function, so it has nice properties. For instance, the sublevel set, the level sets of this function, you can draw level sets of this function, and they're exactly the horospheres centered at this point at infinity. And so this is, so if you had one point at infinity, you have this Busemann function corresponding to it, and up to a constant. So this, you call it h0. If you have another point, you call it h. So this is another point at infinity, and then you have another Busemann function, call it h1. Then what you can try to do is you can say, well, I can try so to connect these points at infinity, what I can try to do is maybe I can try to take convex combinations of these Busemann functions. So take something like t0 h0 plus t1 h1, and try to build a simplex, or in this case, a path at infinity that interpolates between them. Except how do you actually do that? Because this combination is no longer a Busemann function. But there is a way to do that. That's sort of my last point that I want to make. So let me take a ball of radius r around this point for any particular r. This is a ball of radius r. So at this point, the sublevel set where h0 is equal to minus r, this is exactly the horosphere that touches this ball at one point. At this point, oh, this is h1. Sorry, h1 is equal to minus r. At this point, h0 equals minus r is also a horosphere that touches this ball at exactly one point. And to interpolate between them, what I do is I find, so you look at this function t0 h0 plus t1 h1, and if these points are both pi over 2 apart, this function, it's going to be convex and it's not going to have an infimum. So if you look at its sublevel sets, there'll be a point when t0 h0 plus t1 h1 equals constant, where this meets the sphere exactly at one point. And so that lets me define a simplex. Let me call it sigma r in the sphere at x0 of radius r. And it's to a particular t, so t is t0, t1, such that their sum is equal to 1. To a particular t, it's assigning this point. So this is sigma r of t. So in the sphere, it's connecting these 2 points together. And so one thing that is nice about this, it turns out to be Lipschitz. So it's Lipschitz in this metric. And the Lipschitz constant doesn't depend on this r. So then, well, at different values of r, you can have very different looking simplices. But by an Erzela-Ascoli type argument, you can take a subsequence for which, so you can take a subsequence Ri for which this converges to a single simplex on the boundary at infinity. And this simplex, I mean, this definition depended on the initial point. But the simplex in the end will actually only depend on this sequence. It won't depend on the initial point. And it will be Lipschitz in the Tits distance. So this is somehow very nice. And the final thing, so I have 4 minutes left. The final thing that I want to say is that, so what's the point behind using these simplices? The point is that one can prove the following stabilizer bound. So this might be called a Busemann simplex with vertices corresponding to h0 and h1. So one gets the following bound. So the homological dimension of the stabilizer, let me put stab 0 of sigma. So this is the elements in the fundamental group that preserve horoballs at the vertices of sigma. So that really means, one way to say it is that they leave these functions, these Busemann functions invariant. So hi gamma x is equal to h of x. So it fixes the points at infinity, but also horospheres at those points. So the homological dimension of that plus the topological dimension of the simplex is less than or equal to n minus 1. So this is somehow a key bound then that one can prove for these simplices. And so why would you imagine that something like this is true? So let me draw a picture again. So first of all, if you have just a single point at infinity, and you look at the horosphere at that point, so the horosphere at that point is homeomorphic to an Rn minus 1. So if you have a group that preserves this horosphere, its homological dimension is at most n minus 1. So that's OK. So that's exactly right. This is n minus 1. This is 0. If you have 2 points at infinity that are within, let's say, pi over 2, or less than pi is fine. If you have 2 points at infinity, what you try to do is, well, OK, for 2 points, you can take the intersection of these 2 horospheres. And because these vectors are linearly independent, this intersection is going to be an n minus 1 manifold. And if you do this at some other point, it turns out to be the same n minus 1 manifold. So it's, well, it's an Rn minus 2. And therefore, again, this is one-dimensional, but this is n minus 2 dimensional. Now, the last thing that I want to say is that if you try to do this in higher dimensions, this way it will not work. And the reason why it will not work is, I mean, you can have a picture of the following sort. So this is the boundary at infinity. And you have something that looks like a non-degenerate simplex, but it really, if it looked something like this. And then when you looked at it from a particular point, even if it's non-degenerate infinity, it could be that the vectors going to it from a particular point are collinear. So they don't give you a linearly independent collection, and then the intersections of horospheres will look somehow horrible. So that's why, I mean, that's why this is somehow a theorem and not just a lemma. But it turns out that these Busemann simplices are sort of much better adapted to figuring out points where these sort of things are linearly independent than if you use things like geodesic simplices. And I am out of time, so I'll stop.
Yeah, somehow I lost the one very Musemann simplices here in the main argument. So are they
Oh,
the
yeah.
image under F infinity of simplices in P?
So, oops, do I still have this? Yeah, yeah, so I said, okay, so here are points, and they're within pi over 2 of each other. And I said, okay, well, one way, now I have a path, and I need to connect them at infinity, and then push this to that thing at infinity. And you can do this using a geodesic in the Tits metric. But it turns out that the right thing to do is actually not to use a geodesic in the Tits metric. It's to use this kind of Busemann path. And in higher dimensions, you have to use this Busemann simplex in order to get, and there's some other stuff that one needs to do. Yeah. But so the place where it enters is how do you fill in the area between vertices? And the right way to fill it in turns out to be not using geodesics. Or at least we don't know how to do it using geodesics, but we can do it using these things.
The dimension of stabilizer, what is this?
So I really mean, right, so this is sigma. The image of sigma is, so sigma is a Lipschitz map, and the image of sigma is a subset in the Tits metric, so it's really the Hausdorff dimension. So really what you end up proving is that for this Lipschitz map, the image is contained in the image of the, whatever the right dimension skeleton of this. So the Hausdorff dimension is bounded by that.
On the right, but on the left, the dimension of this subgroup is stabilizer.
Oh, that's this on the left. That's the homological. Okay. So, I mean the homological dimension. So, should I say the cohomology? Well, you could say the cohomology. I don't know. Let's see.
In H is HI?
H is, these HIs are, this H is HI. Right, so this is for all I, where I are the vertices of the simplex. And it turns out, maybe I should add, that if if the vertices are all in the stabilizer, then everything on the inside of the simplex will also be preserved by it. So you just need to use a vertex. Like that, it's I equals 1 to k or something. So when the stabilizers, let's say if you take an abelian group in the stabilizer, it's going to be just the dimension of the abelian group, but for more complicated groups. Yeah.
I have one more question.
Yes.
This problem,
Mm-hmm.
this could have been done in the 1980s, right? So could you explain how you can become interested? What is the reason for recent interest in this?
That's a good question. Okay, well, so the thing that was on the board before, so Tam was looking at this for 4-dimensional negatively curved manifolds, and she was trying to figure out what the ends of 4-dimensional negatively curved manifolds can be. And one thing that she proved is that they're always aspherical. And then what we try to do is figure out what does this lead to in higher dimensions. Like what does it upgrade to? So this is, here I said that in dimension n less than or equal to 5, this boundary is aspherical. So the statement that so before that, if n was less than or equal to 4, and you had curvature which was negative but not necessarily pinched, then Tam Nguyen Phan proved that in this case these were aspherical too. And so the thing that we were really trying to figure out was, one thing we were trying to figure out whether in dimension 5 these are still aspherical. Somehow once you get to dimension 6, when you take the puncture torus cross a puncture torus cross a puncture torus, if you take a product of 3 of these and you look at what its boundary looks like, the appropriate thing is a wedge of 2 spheres. So this is not aspherical anymore. So once you go to dimension 6, it's not. So we were trying to figure this out, and somehow the method for proving it ends up giving quite a bit more. And so it gives you the sort of half-dimensional collapse. Okay. So there are different ways to, maybe the last thing, there are different ways to get this point at infinity, so sort of to get this. So somehow, this is something that we all know. This is quite a bit harder. There are different ways to get a point. So the way to get this point is not hard, but the way to show, so you really show that the horosphere at this point is preserved by the centralizer of this element, and out of that you get a lot, namely something like this. So there are several ways to prove this, and I guess one of the ways to prove it is using, so sort of you really have to worry about elements of positive displacement, and for that you need to know that if you take, so one way to do it is to look at the orbit of an element of positive displacement, there's a geodesic ray that tracks it, basically. So this is a result of Margulis and of Carlson Margulis, and somehow, I don't know, I think that's from the late 90s. So maybe there's that. So that's one thing that I can think of. Yeah.
Thank you. Thanks.